Imagine doing everything perfectly. You track every carbohydrate, you exercise daily, and your weight is exactly where it should be. Yet, you wake up and your blood sugar is already surging out of control. This 24-hour glucose trace shows a patient getting 8 hours of rest. The green line remains steady. When the exact same patient, eating the exact same diet, restricts sleep to 5 hours, their blood sugar erupts into severe, jagged spikes. Sleep deprivation initiates a severe, active physiological stress response throughout the body. The loss of those few hours actively breaks the body's glycemic control before the first calorie of the day is even consumed. To understand exactly how this happens, we are going to model the cellular and endocrine cascade of a diabetic patient, restricted to 5 hours of sleep per night for 7 consecutive days. Diet and exercise fail to sustain metabolic health if the body's internal clock is broken. The success of that control relies on two invisible endocrine variables, cortisol and melatonin. These hormones are directly tethered to your circadian rhythm, telling your cells exactly when to store fuel and when to release it. To truly manage insulin resistance, we must recognize the circadian clock as the ultimate metabolic governor. We will start by looking at what is supposed to occur during the early morning hours of a healthy sleep cycle. This animation illustrates the dawn phenomenon. Between 4 and 6 in the morning, your brain releases a surge of cortisol to wake you up. This natural alarm clock signals your liver to release stored glucose into the bloodstream, providing energy for the day ahead. In a healthy body, the pancreas anticipates this hepatic glucose release. It responds with a precise, basal drip of insulin, keeping the blood sugar perfectly balanced. Now let's look at days 1 and 2 of our 5-hour sleep restriction protocol. Because the sleep cycle is cut short, nocturnal cortisol never drops to baseline. Instead, it remains constantly elevated, circulating continuously through the vascular system. This elevated cortisol acts as an active physical antagonist. As you can see here, the cortisol molecules bind to the cell's surface receptors, physically locking the transport doors and blocking insulin from entering. The clinical data on this is severe. A single night of restricted sleep drops systemic insulin sensitivity by up to 30%. A drop of that magnitude renders a completely healthy individual's metabolic response temporarily indistinguishable from advanced type 2 diabetes. And remember, this massive metabolic disruption happens while the patient is still lying in bed, entirely fasted. By day 2, the patient wakes up with a self-inflicted cellular blockade, neutralizing their daytime dietary efforts before they have even eaten breakfast. As we advance to days 3, 4, and 5, the physiological crisis shifts from cellular resistance to pancreatic failure. Sleep pressure directly dictates pancreatic output. Here we have a macroscopic view of a single pancreatic beta cell. Notice these specific docking ports on the surface, labeled MT1 and MT2. These are melatonin receptors. Melatonin acts as a necessary metabolic primer. When it docks into these receptors, it provides the beta cell with the activation energy required to secrete insulin efficiently. But on day 3, our patient stays awake late into the night, staring at a screen. Their eyes are continuously exposed to artificial blue light. This synthetic light actively suppresses the pineal gland's synthesis of melatonin, starving the bloodstream of the hormone. Without circulating melatonin, the MT1 and MT2 receptors remain completely empty. The beta cell drops into a dormant, metabolically unresponsive state. Because it is dormant, the pancreas is physically inhibited from secreting adequate insulin when the patient finally eats a meal the next day. The glucose floods in, but there is no insulin response. We now have a compounding dual threat. The cells are aggressively locking out insulin because of the high cortisol, and the pancreas is failing to produce it because of the missing melatonin. By day 5, the circadian disruption has effectively decoupled the pancreas from the body's actual metabolic demands. We now enter the final phase of the protocol, days 6 and 7 of sleep restriction. The patient is experiencing a paradoxical systemic energy crisis. The bloodstream is saturated with excess glucose, but because it cannot enter the locked tissues, the cells themselves are starving. The brain perceives this cellular starvation as an evolutionary emergency. To fix the perceived lack of fuel, the brain triggers a secondary neuroendocrine feedback loop, specifically targeting appetite regulation. It forces an overproduction of ghrelin, the orexigenic hormone that aggressively drives hunger signals. Simultaneously, it causes a catastrophic suppression of leptin, the anorexigenic hormone responsible for signaling fullness and satiety. The clinical manifestation of this imbalance is intense, uncontrollable cravings, specifically for fast-acting carbohydrates. The patient is now biochemically compelled to overconsume the exact same glucose that their exhausted pancreas is structurally unable to process. By day 7, the sleep-deprived patient has engineered a self-perpetuating cycle of cellular starvation and hyperconsumption, driven entirely by endocrine failure. This diagram illustrates the complete picture of this failure, the circadian glucose trap. It's a triad of dysfunction. High cortisol repels insulin, missing melatonin stops the pancreas, and skewed hunger hormones demand endless incoming glucose. All three of these catastrophic metabolic failures occurred without the patient changing a single variable in their diet or exercise routine. The circadian rhythm provides the foundational infrastructure upon which all other metabolic processes rest. Chronic sleep restriction is, functionally, the biochemical induction of severe insulin resistance. This requires a total reframing of how we approach diabetic management and metabolic health. Tracking carbohydrates and logging hours at the gym is insufficient if the endocrine system remains chemically stressed and hostile to insulin. We have to view an 8-hour sleep cycle as an active, mandatory physiological calibration process, an insulin reset. Restorative sleep is an active state where the body repairs the cellular damage accumulated during waking hours. A complete sleep cycle lowers cortisol, replenishes melatonin reserves, and physically resensitizes insulin receptors across the entire body. This nightly window of restorative sleep is the prerequisite for metabolic survival.
Thanks for watching Body Science School. Please like, share, and subscribe the channel for more.